All right, if you're deep in your GCSE physics revision, then you are in exactly the right place. Today, we're going to build up your confidence on a really core topic, waves. And specifically, we're going to nail the required practical that goes with it. Let's jump right in. Look, we get it. It is totally normal to feel a bit swamped by all the different topics, the equations, the practicals. But honestly, don't worry. The whole point of this explainer is to slice through all that confusion and give you a super clear, focused guide to mastering waves, taken straight from the AQA specification. We're going to make this feel a lot more manageable and, dare I say it, maybe even a little bit interesting.
So here's our game plan. First up, we'll make sure the foundations of waves are rock solid. Then, we'll get into your mission for Practical 8. After that, the scientific skills that examiners are really looking for, how to turn that lab work into precious exam marks, and finally, a super handy revision checklist. Let's get going.
Okay, first things first. Before you can even think about mastering the practical, you've got to be absolutely solid on the basics. I mean, understanding these core concepts is the bedrock for everything else, so let's make sure they're crystal clear in your head. So waves basically come in two main flavors. For transverse waves, I want you to picture a ripple on a pond, right? The water itself just moves up and down, but the wave, the energy, travels outwards. See how the oscillation is perpendicular at a right angle to the energy transfer? Now for longitudinal waves, think of a sound wave. The air particles bunch up into what we call compressions, and then they spread out in rarefactions, vibrating back and forth in the exact same direction the energy is traveling. All right, let's talk properties. Amplitude is all about intensity. It's simply how far a particle on the wave moves from its resting position. So a bigger amplitude means more energy. A really loud sound, that's a wave with a high amplitude. A quiet whisper, a really low one. It's as simple as that. Next up is wavelength, which is represented by that funky Greek letter, lambda. And it's pretty much what it says on the tin. It's the length of one complete wave. You can measure it from the peak of one wave to the peak of the next, or from the bottom of one trough to the next. It's just the length of the wave's repeating pattern. And frequency is all about, well, how frequently something happens. In this case, it's how many complete waves manage to pass a certain point every single second. We measure this in hertz, or Hz. So if you hear high-frequency wave, just think lots and lots of waves are zipping past per second. A low-frequency wave is just much more chilled out and spread out. And this is where it all comes together beautifully, the wave equation. This is an absolute non-negotiable. You have got to know this formula. It tells us that the speed of a wave is just its frequency multiplied by its wavelength. So if you know any two of those, you can always figure out the third. This equation is going to be your best friend in this topic, trust me. Okay, with those fundamentals locked in, let's move on to the main event, required practical number 8. Now, I don't want you to think of this as a chore. Think of it as a mission. You have a very clear objective to achieve. Now, this is really important. This isn't my summary. This is the exact wording pulled straight from the AQS specification. This is your mission briefing. Notice it doesn't just say, do the experiment. It says, make observations, identify suitability of apparatus, and take appropriate measurements. It's telling you exactly what skills it's designed to test. So how do you actually pull off this mission? Well, you can break it down into these 5 logical steps. First, you set up your gear, like a ripple tank. Then you figure out a way to measure the wavelength and the frequency. Once you have those 2 measurements, you can calculate the speed using our new favorite equation. And then finally, and this is the really crucial part, you evaluate your own method. And that brings us to a super important point. The practical isn't just about getting the right answer. Not at all. It's a way for you to show off some key scientific skills. So what we need to do is understand what those skills are and how you can actually demonstrate them. Your final GCSE grade is based on 3 things called assessment objectives, or AOs. AO1 is about knowing stuff, your basic knowledge. AO2 is about applying that knowledge, using equations. And AO3, which is worth a big chunk of your marks, is all about analysis and evaluation. It's about thinking like a scientist, and this practical is the perfect place to hit all 3 of those. Let's make that real, okay? What does this actually mean for Practical 8? Well, showing off AO1 is as easy as correctly defining wavelength. For AO2, you're plugging the numbers you just measured into the wave equation. But for those top-level AO3 marks, you have to go deeper. It's about justifying your choices and critiquing your own work. It's explaining why you chose a 30-centimeter ruler instead of a meter stick. Maybe because the wavelengths were small and a meter stick would be too imprecise. Boom. That thought process, that's an AO3 mark right there.
So the big question is, how does messing around with a ripple tank in a noisy classroom actually help you in a dead silent exam hall? The trick is to see the direct line between what you do in the lab and what you write in the exam. Your hands-on experience is basically the source material for your best answers. Let's see how that works.
Okay, just look at this side by side. In the lab, you measure 10 waves and divide by 10 to get an average. In the exam, you write something like, to improve accuracy and reduce the percentage error, I measured the length of 10 consecutive waves and then calculated a mean. See? That sounds amazing, right? In the lab, you notice the moving waves are just a blurry mess and hard to see. In the exam, you evaluate this as a major source of uncertainty and suggest a brilliant improvement. Use a strobe light and match its frequency to the wave frequency to make the waves appear to stand still. Now that is top-level thinking, and it all comes from the experience of doing the practical.
Phew! We've covered a ton of ground, from the core concepts all the way to exam technique. So let's pull all of that together into one final, actionable checklist. I want you to use this to focus your own revision and just make sure you've got all your bases covered.
Go through these questions and be really honest with yourself. Can you clearly define the two types of waves? Are you feeling confident with the key properties? Can you not only remember the wave equation, but actually use it? And most importantly, can you describe the practical method? And for those big AO3 marks, can you explain why you do things a certain way to make your results more accurate and reliable? This right here is your path to success.
So, there you have it, a roadmap to mastering waves and required practical 8. The real key is to connect the theory, the practical actions, and the exam skills. They all feed into each other. So, my final question to you is this. What's the one thing from that checklist you're going to tackle right now? Pick one, absolutely master it, and then build from there. You've got this.